Welcome back to the next video, everybody. Today's video will be on Langlands functoriality. It will be the first of two videos. So reality check, where are we? Given what we've said so far in chapter 6 of my notes, since global LRC clearly implies both all of the versions of theorem 3 that we've stated so far, and also automorphic Langlands tunnel in the solvable case, it then should suffice to prove global LRC, Langlands reciprocity, and the n equals 2 solvable case to finish our job, to finish the proof of automorphic Langlands tunnel in a sense. But before I do that, there was one last loophole that I said I wanted to close, which was I wanted to show you how a lot of this discussion that we've had in this chapter actually sits inside of a broader framework called Langlands functoriality. So we're going to talk about that over the course of 2 videos, and then we'll finally push towards LRC n equals 2 in the solvable case. So let's recall for GL2 that an unramified representation pi sub p given by characters mu1 and mu2 is parameterized by a semi-simple conjugacy class in GL2 of C, which we called the Langlands class. We called it T sub pi sub p, and it was given by the diagonal matrix whose diagonal entries were mu1 of p and mu2 of p. Let's generalize this. An irreducible admissible representation pi sub p is parameterized by what we'll call a Langlands parameter, rho sub p, from the local Weil group W sub Q sub P to GL2 of C. And what does the LLC say? What does local Langlands say? It says that the same thing actually holds for GLN over any local field, which we'll call F sub V. Okay. In summary, every nice representation, pi of GLN of F sub V is conjectured to be attached to a unique parameter rho sub B from W sub F sub B, the local Weil group of F at B, to GLN of C. And it's not just that these things match up, it's that certain, quantities on both sides of the correspondence, like epsilon and L factors match up, blah, 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 blah. Okay, nice representations pi of GLN of FB sort of match up locally with representations of local Weil groups of F sub B. Okay, so let's generalize a little bit. If G is an FB reductive group, we defined reductive groups a few videos ago, the L group LG is meant to take the place of GLN of C in that description above. So it's meant to take the place of GLN of C in the sense that it will now be the thing parameterizing irreducible admissible representations of G of FB. Okay, so loosely speaking, what should happen then? Well, every nice representation of G of FB should be attached to a semi-simple homomorphism, whatever semi-simple actually means here. Phi from the local Weil group W sub F sub B to LG. If LG is supposed to take the place of GLN of C, then LG should show up right here. Okay. In the case we're dealing with so-called unramified representations, which we'll define in a moment, what should this amount to based on the discussion we just had? It should amount to fixing a special semi-simple conjugacy class in LG. And what should we call that? Well, we should probably call it the Langlands class or the Langlands parameter or something, and we should probably notate it T sub pi sub B. And we should think of it as canonically attached to pi sub B. This is exactly what we did when we were specifying to the GLN case, right? Okay, so what is the L group? If G is defined over a local or global field F, LG is just going to be some group of the form, let's say G hat semi-direct product, the Galois group G sub F. And what is G hat? It's the complex Lie group, which is dual to the so-called root datum of G of C. And I won't really define root datum or get too far into this. Okay. And we also want to require that the action of GF on G hat is trivial if and only if G is so-called split over F. And I will define terminology like split and quasi-split and things like that in just a moment. Okay, and you should see Borel automorphic L functions for far more details. In fact, Borel-Castleman might be just a good read if you really want to get into this stuff. So sometimes the Galois group of F is just replaced by some Galois group of E over F, where E over F is just some Galois extension. Over which G splits, you can't take any Galois extension. The point is, if you do that, then the Galois group of F bar over E just acts trivially on G hat. And so if you do just take LG to be G hat semi-direct product, that Galois group of E over F, you still have a complex reductive Lie group. Everything still works. Okay. Here's an example. If G equals GLN is F and F is local or global, just take LG to either be GLN of C, or if you want to use more generally Galois groups of E over F for any E over F Galois, you could just take LG to be GLN of C over the Galois group of E over F for any E. I mean, this is exactly what you expect to happen, right? We're supposed to be generalizing this case, so it better be that the L group can be taken to be GLN of C, right? because that's the L group was supposed to function like G ln of C functioned, remember? Okay, it's convenient to think of the L group in a slightly different way, or maybe to generalize a little bit. We can define the L group of G, LG, to be G hat semi-direct product sigma, where sigma is now any group actually, equipped with a homomorphism into the Galois group of GF. It doesn't have to be GF, but just some group that is equipped with a homomorphism into it. For example, like the Weil group, W sub F. We will almost exclusively deal with and think of L groups in this way, just because we've been working with Weil groups so far. Why not be a little bit more general? So now what about all this terminology I promised you? Okay, so first of all, a torus over an algebraically closed field K is just something group isomorphic to the K group scheme, the multiplicative group GM to the N for some N. Okay. If G is a linear algebraic group, a maximal torus in G is a torus in G, which is not contained in a bigger torus. Wow, surprising, right? For example, the group of diagonal matrices in GLN over K is a maximal torus because it's isomorphic to GM to the N. This is kind of the example you want to latch onto when people start talking about tori in the linear algebraic group sense. What if K is an what if K is an arbitrary field? Well, what should a torus over K be then? I mean, I can only think of one definition. It's a linear algebraic K group whose base change to the algebraic closure is isomorphic to GM to the N for some N over K bar, right? So then what is a split torus over K? It's something that's group isomorphic to GM to the N over K itself, regardless of whether or not K is algebraically closed for some N, okay? So a split torus just means kind of your isomorphism descends to be over K instead of over K bar, okay? I also owe you some other definitions. I owe you some definitions of like unramified reductive groups. So we're going to be assuming that G is unramified over F. F is our local or global field. What does that mean? It means G is quasi-split over the local field F and split over an unramified extension E over F. What does all that mean? It really just means G contains a split maximal E torus. That's it. Okay. So we're going to be assuming that. All right. And what is E? E over F is unramified. So that's why we call G unramified over F. All right. Now, for such a group, so for such an unramified group, so just think GLNF, for example, when should I call an irreducible admissible representation unramified? This word unramified, if you haven't noticed, gets thrown around in number theory all the time in all different subfields, but it always sort of it means the same thing. It should mean that when I restrict to a special, whatever that means, maximal compact subgroup, so think GLN of OF, the ring of integers of F in this case, in our special case that we're trying to latch onto, that better contain the identity representation with multiplicity 1 somewhere in its decomposition into representations, into sub-representations. Okay. I mean, unramified always just means when you restrict to some special subgroup, something is trivial somehow, okay? Just loosely speaking. Now, what about the kind of the set of unramified representations of G of F as a whole? If Frob denotes the Frobenius generator for the Galois group of E over F, the unramified representations pi of G of F are in bijection with the semi-simple LG0 conjugacy classes T sub pi and LG0 semi-direct product Frob, which is something that lives inside the L group. What is this LG0? It's just the identity component of LG. It's the component that contains this connected component that contains the identity, because this is a group, right? Okay, so, well, you have this bijection, right? The bijection matches up each pi with, I guess, this conjugacy class T sub pi, right? Well, to each unramified pi, then we're attaching some T sub pi, and that T sub pi is going to be what we call the Langlands class. And what is it? It's just G semi-direct product Frob in the L group of G, okay? For some G, okay? And it's in terms of these classes and their matrix representations that the L factors from earlier videos were defined. This is the T sub pi that we were talking about several slides ago, in other words. This is the thing that's supposed to take and generalize the notion of the local Langlands parameters that we defined earlier, okay? And so we'll push towards the actual statement of Langlands functoriality next time. We'll start looking at representations of L groups and their properties, and then we'll just make the statement and we'll move on from this topic, and we'll finally start looking at solvable LRC in the case n equals 2. So I'll see you tomorrow, and thanks for watching.